In this lecture today, we will be addressing the issue of inverse functions. The definition of inverse functions: f and g are inverse functions provided that the range of values of each function is the domain of the other, and roughly speaking, you can think of this as they undo one another. So f of g of x is x, and g of f of x is x. Here we include the domain of the domain of g, so all the x's that are fair game to feed to g. And here we specify the domain of f, so all the x that are fair game for f. So let's look at an example. First example, these two functions are inverse functions of one another. And the way we can check that, first let's check the domains and the ranges. So the domain of f is the whole real line, all the real numbers. Also the range of f is also all the real numbers. So think about what the graph looks like. So we have y equals 2x. So it goes through the origin, rise 2, run 1. So this is our f of x. And we see its domain as the whole real line. You can plug any x in. There's no x that you can't plug into this. And you can get any real value as well. If we look at g, we actually have the domain of g also being all the real numbers. So there's no number that you can't plug in, no real number that you can't plug in here. We know its graph. Now we have x over 2, so just goes through the origin, rise 1, run 2. So this is our g of x. We see also in this case, you can get any y value with this line. So its range is also the whole real line, or all the real numbers. And the key thing to note here is that the domains and ranges sync up. So in the definition we said the domain of one has to be the range of the other in both cases. So that criteria is satisfied. And now we look at f of g of x. The outer function here is 2x. So this is going to be 2 the inner function is x over 2. So we're plugging x over 2 in here. So maybe an easier way to see this would be, this is going to be f of x over 2. So when we plug x over 2 in here, we get 2 times x over 2, or x. So we see that the functions undo each other in this order. How about in the other order? G of f of x, that's g of 2x. So we plug 2x in here for g. So we have 2x over 2, or x. And we see that all the requirements in the definition of inverse functions are satisfied here. Going back, the functions undo one another, and the domains and ranges match up as specified. With this example under our belts, let's take a look at what happens if we graph the line y equals x and we'll note my drawing's slightly off here. But what we want to notice is that the graphs of these functions are mirror images of one another about the line y equals x. And that's always true for inverse functions. So the graphs of y equals f of x and y equals g of x are symmetric about y equals x. So again, that's a property of inverse functions. If we look at another example, f of x equals x plus 1, g of x equals x minus 1. And again, we can see here that the domains and ranges are all the real numbers. And again, if we graph them, y equals x plus 1. So this is just y equals x shifted up 1 unit. And then y equals x minus 1 is y equals x shifted down 1 unit. So again, we see that these functions are symmetric about the line y equals x. And again, we can check. So f of g of x, plug in x minus 1. So replace that g of x with x minus 1. So that means we plug in x minus 1 here. So this is x minus 1 plus 1, or just x, which is what we want. Going the other way, g of f of x, so replace that f of x with x plus 1. And we plug that x plus 1 into the variable for g of x. So we get x plus 1 minus 1, or x. So again, we see that these are inverse functions. Okay. Let's try another example. F of x equals 1 over x. This is an interesting example because its inverse will be itself. So let's recall what this graph looks like. Or maybe first we can check. Let's check this condition. F of g of x. So that's f of, plug in g of x here, f of 1 over x. Plugging this 1 over x in here, in f of x, gives us 1 over x, which is x. And if we go the other way, it's the same thing. So g of f of x, replace the f of x in here with what it is, 1 over x. Plug that 1 over x in for g. What we get, 1 over x, or x. Now the domain of 1 over x is all the real numbers except 0. What about the range? Well, think about the values you can get. You can get any positive number, you can get any negative number, but you can't get 0. There's nothing you can put in the denominator here that would make 1 over x 0. So the range is the same. Which it would have to be if 1 over x is going to be its own inverse. Remember, the domain of a function has to match the range of its inverse. And the range of a function has to match the domain of its inverse. Okay, so we've confirmed that 1 over x is its own inverse function. But remember that the graph has to be symmetric about y equals x. So what does that mean in this kind of weird example? Well, think about 1 over x. Remember that it looks like this in the first quadrant, and then it looks like this in the second quadrant. Now, take that graph and reflect it about y equals x. What do you get? Well, if you reflect this top piece over y equals x, then you're going to get this piece here. If you reflect this bottom piece about y equals x, you get this piece here. So all I've done is just draw over the graph. And the same thing would happen down here. So even when you do the reflection about y equals x, you get the same graph. And that is an illustration, graphically, of how 1 over x is its own inverse function. Okay. Another example, y equals x squared. So let's think about what's happening with this function. And right off the bat, let's think about graphing it. So this would be our f of x. And the issue now will be, what happens if we reflect this about y equals x, like we've been doing here? If we do that reflection, what's the problem with this purple curve? Well, it should be clear, this is not a function. This purple curve does not pass the vertical line test. So this curve fails the vertical line test and is thus not a function. So the issue here, the reason this fails the vertical line test, is because f of x fails the horizontal line test. So graphically, y equals f of x must pass the horizontal line test to be inverted. So y equals x squared does not have an inverse. However, if we restrict the domain, and by the way, you can also see here the domain of y equals x squared is all the real numbers. Well, this isn't even a function, so it doesn't have a range. So I guess it's not worth mentioning. So right, this one is broken because it fails that horizontal line test. But what we do is we can restrict the domain and still do something. So define, we'll call it f plus of x to be x squared for x greater than or equal to 0 and f minus of x to be x squared for x less than 0. We can even stick with less than or equal to 0. Now in this case, and we're going to use some new notation, f plus has a domain. We're only feeding it non-negative real numbers, so we only can feed it numbers in 0 to infinity, and its range, well, x squared will always be 0 or greater, so its range is 0, infinity. And again, this is new notation that comes in handy for this type of work, where we say this is the domain and this is the range. So roughly speaking, the way this is written, we want to think of this as, this tells us that the function f plus takes numbers from the interval 0, infinity and maps them to numbers in the interval 0, infinity. So let's invert that function. So we know y equals x squared looks like this. I should say this is y equals f plus of x. And when we invert that about y equals x, we have the function that looks like this. And you could probably guess what this function is. G, we could call it g plus of x. It's just the square root of x. That's this. And you can think about the domains and the ranges. G plus, well, we can only feed numbers that are greater than or equal to 0 to G plus, and then it spits out the positive square root. And you can see that it's the range of G plus, or the range of f plus matches the domain of G plus, and the domain of f plus matches the range of G plus. Kind of easy in this case because all four of these are the same. But we can then check that, in fact, these are inverses of one another. So to check, we take f plus of g plus of x, which is f plus, so g plus, we said, was the square root of x. So we're plugging the square root of x into this f plus, which is x squared. So this becomes we have root x squared, which is x. Going the other way, we do g plus of f plus of x. Again, f plus of x was x squared. So this is going to be g plus of x squared, or g plus is the square root function. So the square root of x squared, or x. And this tells us that the functions are inverses of one another. So in order to do some type of inversion with this function y equals x squared, we had to do a domain restriction and look at just this right piece, the piece in the first quadrant. We could also use the other piece. We can do that on the next page. So suppose we defined, well, we did define on the previous page, we had f minus that was x squared for x less than or equal to 0. And so if we draw the picture for this one, this is our f minus of x. And if you think about inverting this, what will that look like? Well, we want to invert again about the line y equals x visually. So when we do that, we are going to get something that looks like this. So that will be our g minus of x. And that, of course, is none other than the minus square root. For x greater than or equal to 0. So check again the domains. So this g minus takes, what's the domain of this? It takes non-negative x values and maps them to values that are less than or equal to 0. So it maps them to minus infinity to 0. Now how about our original f minus of x? So f minus was this restriction of x squared to the second quadrant. Its domain are the numbers from negative infinity up to 0. And its range are non-negatives, so numbers that are greater than or equal to 0. So 0, infinity. And you note that what we needed were the domain and the range of these pairs to match. And they do. So this is a non-trivial example where we actually see the domain and the range of these pairs matching. Now we can check to actually see that these are inverse functions of one another. So let's look at f minus of g minus of x. So that g minus, by definition, is minus root x. So plugging that minus root x into f minus, so we square it, and of course, if we square the negative of square root of x, we get x. And going the other way, replace the argument in here with f minus of x. F minus is x squared. G minus of x, so we plug x squared into g minus of x. That was the negative square root. So we get the negative square root of that x squared term. which is no, right. It's a little bit subtle. Note that in this case, remember, this x is negative. Which means why don't we do it this way? We'll rewrite it as the square root of negative x squared. Clearly nothing's changed here. But because x is less than 0, less than or equal to 0, that tells us that negative x is greater than or equal to 0. And again, this all comes back to the fact that we're pulling the x from over here before we feed it to f. So the square root, when we square this, the square root chooses the version of x here that's positive. So rather than returning x, which is negative, it'll return minus x. So we get minus of minus x, or x. A little bit of a subtle detail there. But it all comes down to the fact that when we get the square root of something, it's giving us the positive square root. In this case, x is actually negative because of the domain of f. And that means the square root returns minus x, so that this minus x is positive. So this, in fact, confirms that these are inverse functions. So this illustrates how when you have a function like y equals x squared that doesn't pass the horizontal line test, intuitively, again, if you don't pass the horizontal line test, when you reflect about y equals x, the graph doesn't pass the vertical line test for being a function. So that's why we have this horizontal line test. But it doesn't mean you can't do anything. You just have to restrict your domain so that when you do the restriction, your function does pass the horizontal line test. So its reflection will pass the vertical line test. So this is the idea of inverse functions. What we will focus on in the next lecture is inverting our exponential. So if you recall, when we studied exponential functions, remember the graph of any exponential function, this will be the case where a is greater than 1. Any exponential function looks something like this with this y-intercept of 1. And we will now, in the next lecture, we'll look at reflecting this, and we will get a graph that looks like this. And this is what will be the log of base A. And so we will look, now that we have the tool of inverse functions at our disposal, we can take any exponential and find its inverse, and its inverse is called the natural log. And they will have this property that they undo one another.